All right. Okay, so where we left off was talking about Google and their architecture and their setup, and we're gonna just move ahead to here. So we've established that Google has a number of data centers all around the world. So I'm gonna draw a little map, a very, very small scale map. So we're gonna have one here, and one here, and one here, and you know what? I'll do two more. I'll go all the way around the world. So we'll start over here. This one is Tokyo, and this is LA, and this is Chicago, yep, and NYC and London. These are arbitrary. I am not, I think it's probably unlikely that Google has data centers in these large urban areas, right? Probably close to them, but the real estate costs and all that is pretty high. So I don't know, but I do know we looked up where the Fortnite server, my son and I, because my son was complaining about his ping time, and I said, well, you know what, we can find out where they are, and they're located in some shithole Rust Belt town in Ohio for North America East. Why? Because it's cheaper, right? Yeah, that's why. So I mean, if anybody, whatever. So I said to my son, look, even if we were right next door, your ping time wouldn't be that much better. It'd be, it's already like 15 or 20 milliseconds. I said, yeah, it might go down to like 10, but you're not going to go pro just because you live in Ohio. Anyway, all right. So anyway, Google has a bunch of data centers, and we're going to, for purposes of discussion, we're going to say they're in these places. Now, there's a few important things to remember. And I'm going to go through them. So number one, the index is really big, and data centers only hold part of it, right? We can all understand this index is very, very big, and if everybody held not only the index, but all the stuff required, to make the index locally useful, that would be a lot more than they need, right? Because they mostly don't need it all. For example, Tokyo, what language do you think most of their requests on Google are? Probably Japanese, right? So do they need the entire English language index? Probably not. The entire French language? Probably not, right? Wouldn't make sense. I mean, I'm sure they get the occasional English or French language query, but it's unusual, and it's certainly not worth the trouble to hold the index there, okay? So that's two. Data centers only hold part of it. Number two, it is not clear that Google maintains master copies of the index for its entries, right? Certainly, index entries are going to be replicated, right? We talked about how anytime you have some data, in order to know that, it's correct, you need a triple copy, right? This is one of the things we talked about in Facebook. So for sure, Google has multiple copies of any index entry. It seems unlikely that Google would arbitrarily say, this one is the master copy, because what if the master copy itself gets a defect, right? Then you just echo that defect onto all the other copies. That would be bad. So, it's not clear that Google maintains master copies. You can come up with a good argument for why they shouldn't, but, they don't really tell. But there's that, okay? So 3, Google would prefer to locally fulfill queries, right? If somebody asks a search question, it's obviously faster to answer it with what you already have, but data centers hold references to non-local entries, all right? What does that mean? Well, suppose you enter in a query on Tokyo. You're in Tokyo, and for some reason you enter the query IDS 200 Lundquist spring 2023, right? Not a query that Tokyo is likely to have already cached because they've gotten a bunch of them already, right? So what's going to happen? Well, Lundquist, for example, that's probably something they're not going to have in their database. They're going to kick that over to wherever else that might be. So if there's an index entry that they don't have the actual entry, they have a pointer to some other data center that says, hey, here's where you go to look for that. Now, number 4, responding to local and non-local queries may work differently. Okay, so here's the other thing. Suppose Spring 2023 is common enough that it actually is stored in Tokyo's data center, right? But these other terms aren't. So what that would mean, number 1, LA could ship over the entire index entry, which might be very large, right? That's going to take some time, right? Even on a fast connection, if we're talking some gig, that's going to be some time to do. So what probably happens is that the two parts of the query are computed separately. Tokyo computes locally the part that it can, says, oh, here's the matches we have for that. LA computes the part that they have locally and sends the finished results back, right? Basically some like top list of matches that then Tokyo can integrate into its results. We don't really know in detail, like obviously, if you have everything there at a local data center, like maybe at Chicago, IDS 200 Lundquist Spring 2023 is a request Google has seen before, right? They might have that cached, they might probably not. They might have, but all those elements locally stored anyway, and they can fully process that query at the Chicago data center. For Tokyo, if it's split, they might opt for speed rather than perfection, right? So this is one of many cases we'll see. If it's a query that doesn't come up that often, like this one surely would not in Tokyo, Google says, you know what, this is a one-off query. Everybody knows that search isn't a perfect thing. We'd like to give you the absolute best results we can, but we'd rather give you pretty good results within half a second. And that's what they're probably going to do. But again, this kind of stuff is Google's special sauce. They don't really give a lot of detail. But key things, index is really big. No data center holds the whole thing, right? They only hold part of it, and the part they hold is what's locally relevant, okay? Number 2, as far as we know, different copies of any part of the index are pretty much equivalent. Chances are a data center that holds a copy of one index entry probably holds replicas of it there, but it's possible that one data center could hold one copy and another data center could hold another, okay? And obviously, Google would prefer to locally fulfill queries when it can. If it can't, it's going to ask around and say, oh, I see that this entry is stored at this other location. Okay, so there is sort of a hierarchy involved, but it's not really, there is one supreme data center over all the others. It's simply that there's a bunch of different data centers. If a request can't be processed locally, it gets kicked off to another one. Okay? Okay, and that's what a lot of these early slides are getting at. Okay, so again, right, we know data centers have different capacities, different stored content. They don't all hold everything. They hold what's locally relevant. Same reason as Facebook, basically. So if a page isn't stored in the local data center, it has to be retrieved from another data center, right? The local index contains that information. But what can also happen if a query becomes popular or an index entry becomes popular in that sense, like for some reason, there's a lot of people doing requests about UIC type courses in Tokyo, then yeah, at some point, eventually Google will start storing that information locally at the Tokyo data center. And the way that works is basically the same. Remember the hybrid memory model we talked about way back when? I'm going to draw that picture. So I know you all remember this. So you have RAM, which is fast, and you have disk drives, which are slow but cheap. Everybody still with me? Disk drive slow and cheap? Yeah. Yes. Okay. All right. Let me draw a couple more. I wish I could set it to be a default transparent selection. Okay, so that's our disks, right? And remember how the hybrid system worked is that if you have a query for popular data, you can respond to it, popular data stored in RAM because fast, okay? Less popular data stored in disk because cheap, okay? Okay. So a request comes in. If you can fulfill it in RAM, you certainly would because it's fast and people want that. But if it can't get fast, it gets sent to disk because the disk definitely has it, right? And this is the same thing. If a request comes into a data center, right, whether it's in RAM or not in RAM at that data center, it can be fulfilled locally, right? So I'm gonna cross that out. Okay. Local fulfillment, if possible. Okay. Otherwise, non-local, right? Because you know it's stored somewhere else. And the reason why is basically the same, is that all of these data centers have finite capacity, right? It would cost a whole lot of money for every data center to have a complete copy of the index. And most of the time it wouldn't be to any real purpose because you'd be storing a lot of information that would almost never be looked at. So Google kind of made that decision. But again, same kind of idea here. So we're starting to see things repeat. Okay. Now, Google stores a replica for every page that its spiders have visited, right? It stores both the original pages and data that extracts from them and then compiled it in the index. So it has those three big kinds of data. So, but the set of pages themselves, the raw page data, obviously that is pretty big, right? That's going to be like the entire surface internet. That's really big. So Google is not going to copy the entire index and the whole set of page replicas to every data center. So it's really expensive and it's not worth the trouble. So instead, data centers will store pages predicted to be of greater local interest, right? So things about local places, things about people, things about in the local language. And in fact, that's generally the first pass for determining whether a page will be locally stored or not, is Google looks at the language. Google looks at the language and says, this page is written in Japanese. We're going to put that in the Tokyo data center. If there's a page written in English, for example, like it's some baseball thing about the World Series, that's probably going to be of interest to all the American data centers, right? At least of enough interest that it'll get stored there. So pages can definitely be stored at multiple data centers. Different pieces of the index can be stored at multiple data centers, right? Which makes sense because you want to fulfill this stuff locally. And it's very possible that, you know, the search terms World Series 2022 have come up at every data center in America, right? Many, many times over the last month. Okay. Anyway. So, as far as caching, just like Facebook, Google also has to deal with the long tail popularity problem. That means basically even distant events are surprisingly likely, more than you would expect, right? So if Google's problem were just that people only want to look at pages from the last day, that would be a lot easier one to manage. But of course, people will often bring up content from far back, right? So a lot of Google requests, sure, are for things that are currently significant in some way. But people look up, you know, stuff about old movies. People look up historical data about things. People go reference old articles for whatever reason, look at old pictures that have been up for a while, right? That sort of stuff happens all the time. A substantial minority of Google searches are involving, well, I mean, are dominated by very old pages, right? So obviously any search, right, if you're doing something like search sports, that's going to return a lot of older pages. It's going to return a lot of new pages, but a lot of older ones too. But Google is always looking at older pages as well. Perpetual novelty. A surprising fraction of Google searches are for first-time ones that Google doesn't have index entries for, hasn't ever seen before. The most recent stat I have on that as a factoid was 15% in 2013. In 2013, 15% of Google searches were ones that Google had never seen before. And if you think about what those might be, my best guess is they're like names with other oddball combinations, right? So for example, if I start teaching a new course here, if they assign me to teach IDS 410 in the fall, there are going to be a bunch of searches involving Lundquist UIC IDS 410, right? And variants on that, you know, which section or what's the course about or Reddit or stuff like that. Anyway, and anything can work like that. People are Googling aspects of themselves, you know. Yeah, so a lot of new queries are going to happen. Anyway, the key thing, number one, just like in the hybrid system, hybrid RAM and disk system, Google needs to keep its performance going by continually updating and caching search results, right? Just like, see, this is why I bring up this picture. Just like here, stuff that used to be popular could become popular again, right? For example, suppose some old song gets reused in a movie, right? Like Disco Inferno gets back in a song, and then suddenly people start looking up Disco Inferno on this. Yeah, it's going to go back into the cache stuff. Okay, there was a window. Disco Inferno was a song from the mid '70s that was, I guess it was big for a while, but then it came back for a little while in the late '90s. It was starting to get used in a bunch of movies. So yeah, that happens. It'll be kind of weird for you guys when that happens. Well, all this stuff that's popular now, like 30 years from now, you'll be taking your kids to the movies because you'll be like, oh man, I remember that song. Yeah. Anyway, I know I'm in the target demographic. Shit, we watched that Thor: Love and Thunder, was it? Yeah, it took my son to see that, and I was like, the whole soundtrack was basically late 80s. I think they had like 3 Guns N' Roses tracks in there. I'm like, wow, I feel personally targeted by this. Yeah. Anyway. Okay. Anyway, so as far as task division, right, there's some stuff that happens the way Google does it. So again, let's assume Google has gotten a query and has determined they're going to handle it locally, right? So that we get that out of the way. This data center is going to handle this query. So first thing, Google's going to see, is this thing cached, right? Has somebody recently done this query before? Do I have the results already available? If so, we use them. If not, we got to do the process, right? And the process is first, number one, look through the query terms and see what index entries are going to be involved in delivering the search results. Second, pull the page data out of the system and rank those pages against each other, okay? And then eventually construct a web page with those search results, deliver that, at least with the first page of web results, first page of search results, and deliver that to the user. Now, interestingly, right, we know this, many pages may be associated with a particular search term. So you can often, if you search in, you know, for a bunch of different popular terms, you could get many billions of pages. And if Google went through the detailed process of cross-ranking all of them against each other, I'm going to mention this. Number one, because some of you may be wondering how to do this, right? If, I'm going to say, it would not be feasible for Google to fully rank the entire list of search results in order. Reason why? Because you got to cross-compare everything, right? I mean, there's ways to make it faster. You can, you know, give it values and drop things in bins and kind of work with smaller stacks, but it's going to be really slow to sort that entire list if there are like many billions of pages. But fortunately, Google doesn't actually need to do that. So that's a good thing. Now, we're going to do a little, first of all, suppose I run a query on, I don't know, Chicago Cubs World Series 2023, okay? I run that World Series query. How many search results is Google actually probably going to deliver to me? What's that? 5 million? They're going to deliver me 5 million search results? They're going to deliver to me. They are going to arrive on my computer. That would take a while, wouldn't it? Yeah, that's not going to happen. How many are they going to send me? Probably more than one. Ballpark number, I would probably guess a few hundred. Somewhere between 100 and a few hundred, like 300 or 400, is going to be correct for the vast majority of searches. Okay? Because that's what they do. Google's kind of like, well, these are the best matches we have, and we've pruned out the redundant ones. So like if there are multiple pages that are substantially the same, Google's going to kind of ignore them. Google's going to say, like, for any one kind of page, they're going to give you the best one. So anyway, yeah, Google's just going to send a few hundred. But let's keep them simple, and let's say they're going to send me 100 pages. Okay? Now, we get into the hardware issue here. I'm going to talk about parallelism, because everybody likes parallelism, whether you know it or not, because this is what makes our life better. Okay. Right? So everybody sees what I'm drawing here. This is the process. Right? It's not an onion on a string there. It's or garlic, whatever. Okay. So here we have query arrives, right? Index entries determined. So however Google does that, we'll get to that in a bit, but Google figures out what index entries it's going to use to fulfill this query, and then breaks entry into segments, runs ranking in parallel. Okay? This sounds familiar, I hope? All right. Now, suppose this query, right, delivers a billion search results. And suppose that Google wants to deliver to me the best 100 search results. And suppose that this query is distributed over, say, 1,000 servers. This index entry is broken up into 1,000 segments. How many search results does each machine need to send to guarantee that I will get the 100 best search results? Every one of these gets a segment of the list, does the ranking algorithm on it, and then returns back its ranked list. How many does each one of those 1,000 machines need to send along to guarantee I get the best 100 results? You got lost in the numbers. The answer is actually much simpler. 100. Because if every one of those devices sends me their top 100 and they all get recombined at the end, it's metaphysically certain that I will have the top 100 results in that short list, right? Everybody see that? Okay. So the problem, like I said, Google doesn't need to rank that whole list. Google just can say, well, each of us is going to send the top 100, and it doesn't even need to sort that entire list in order. It just needs to have like a threshold for what the top 100 is at any given point. And if a better one comes along, that changes the threshold, and Google says, well, I can ignore you. So it just goes through the math and says, okay, at the end, I scan through that entire list. I have the top 100. I can send them along. Now, having said that, there's the trade-off between speed and perfection. Always there is this, because we understand the search engines are not perfect, right? Sometimes they deliver us some mildly junky results. And Google might say, look, I'm only going to send you like 1,000 search I'm only going to send you 100 search results. And I got 1,000 machines doing the work. Suppose I want to guarantee to get you the best 10 results, right? The best front page. I could have every one of those machines say, here's the best 10 we found, right? And it's a metaphysical certitude that that front page will have the best 10 search results that Google can give me. Second page, it's probably still going to have most of the best results, right? But that's going to be a little bit faster, isn't it? It's going to be a little bit faster for each one of those devices to just send me their top 10 rather than everyone to send me their top like 300 or 400 and have to do the recombining and the reassembly and the shipping out, right? Everybody see that? So yeah, this is, It's not exactly certain all the details that go into how Google makes this decision, what happens, whatnot. But what we know, it's certainly feasible. Since Google only sends us a few results, that simplifies the problem a whole lot, right? And number two, Google, in many cases, because we know Google loves speed, Google might very well optimize for a shorter list in order to give the results back faster, right? You'll say, well, you know, you're going to get 98, based on randomness and statistics and what, you're going to get 98% of the top 100 results, but we know for sure you are going to get the top 10 best results, and that's what you really care about, because most of these searches get fulfilled on the front page anyway. Okay, so would you like to know more? I hope all that made sense. So what I'm trying to do here is give you more background of how all this stuff works. This is not the level of detail you will really need to know on the exam, but if you're following along with this and understanding, you know, you have kind of these narratives of how Google works, and you'll be able to make more sense of what's going on the exam. That's why we're doing this. Okay. Okay. Now, as far as Google's indexing system, it's basically built around three different roles for servers. Number one, there are index servers, right? Index servers hold the index entries, and the index entries are often very large, and they are often broken up into segments and stored across multiple servers. We'll talk more about that in a minute. Second, document servers. Document servers, number one, they store the complete web pages because Google sometimes needs to have those on hand, but they also extract data from the web pages, right? They're used as a point to extract data from the web pages, so that Google has that extracted data on hand, ready and available to be used for page ranking, okay? Spelling servers, finally, are used to check alternatives because people make mistakes, right? People make mistakes writing in search queries, and Google wants to be able to detect those. So the process following a query, right? Query rolls in, Google says, oh, I have this query, what am I gonna do? Well, first, Google needs to figure out which index entries are going to be used. First of all, exact text matches, those are always gonna be part of it. Number two, semantic matches, right? Or we say nearly exact, for example, plurals of words, right? So if you tried Google in 1997 and you typed in, you know, Doug Lundquist IDS course, I don't know, I shouldn't really be using myself in so many examples, but if you did, well, number one, you wouldn't get anything because I wasn't teaching anything in 97. But number two, right, it would only show up the exact word course, not even like courses with an S, right? Because that was, but these days they say, oh, you mean course, we're going to include courses as well, because that's like close enough. And also there are going to be spelling servers for alternate meanings. Once it's figured out which index terms it's going to use, it should retrieve the web page data based on those search terms, and then finally deliver the ranked matching results as, you know, our format we're used to, a link plus blurbs on all of them. Now, I do have a link to an early paper. This is Google's thing from circa 1997, Anatomy of a Large-Scale Hypertextual Web Search Engine, right? Basically, how you can find stuff on web pages. Now, at this point, oh, you need screen. I use control for this. This took me a minute. Boom. So this was their early paper. This is an academic research paper about, you know, hey, this is what we're going to do for Google. If you scroll down long enough, you can find some interesting details about how it actually works. We're not interested in all this stuff. You can read it if you want. It's not too hard to get through. But a couple things. Number one, it had a system of about 150 gigs, which sounds like not very much now, right? You tuck that away in a corner of your hard drive now. But back in those days, you know, when I first moved to Chicago in '98, I got my Windows XP machine, and it had a 6 gig hard drive, and I was very excited to have it. So this is like a few dozen hard drives probably. Okay, so it's not a huge system, but it's not trivial either. Anyway, and they have a bunch of documents stored on those hard drives. Now, their problem was, how do we figure out how to get this result fast, right? We know the web is big, we know it's getting bigger, we're kind of limited by the technology we have. Popular results we can store in RAM to a point, less popular stuff we got to keep on disk. So, and I should add right now, 150 gigs would not even be a significant challenge know, as far as system architecture to do that all in RAM these days, right? I mean, 64 gig machines they're out there now, they're available. All you got to do is bundle a few of them together, which is not going to be that big of a challenge, you know, for guys that do that sort of thing. Okay, well, we had some queries here from the late 90s, back when Al Gore was vice president, and you'll see here, you know, the difference between cached and not cached. So the initial query took about 2 seconds there, right? If it were cached, that went down to a blindingly fast 0.06. If we did the query for vice president, that took closer to 4 seconds. Having it cached cut it about in half. Now, the interesting thing, this really shows the split between RAM and disk access, right? So the CPU time, basically you can think of that as the RAM processing time, right? Whereas the total time, the vast majority of that is due to reading off the hard drive because hard drives are slow. So if we have this query cached, you know, the total time becomes very close to the CPU time initially. Right here, the cache time very close to the CPU time, very close, very close. But the vast majority of savings are simply that you're not reading from the very slow hard drive, right? So this one here, you know, 0.06, what is that, about 30 sometimes faster? This is about, I guess, 20 times faster. This is almost 10 times faster because it's not looking at the disk for this stuff, okay? But, you know, the question is essentially for some of these more common results, they're going to be ranked higher. They're going to be stored in parts of the machine that are easier to get to. So Al Gore was a significant person in the 90s. And so, you know, it was a popular search. They prioritized that one. Search engines, vice president, they were low popularity searches, so they weren't as prioritized, and the time speed is actually pretty slow. Anyway, so yeah, and it turned out to all work pretty well. But if you're interested in this stuff, you know, there they are, and now they have billions of dollars. Okay. Okay, so index servers within any data center, they're going to be grouped into clusters and operate divided by language, right? So in general, search queries come in, they're going to be in one language, and Google's going to treat them as if it's all in one language. Now, just for English alone, there are probably several 100,000 terms, right? If you take just ordinary words, there's probably around 150, 200,000 words. Start adding on place names and you know, numbers and people's names, then, you know, it's going to add a lot more. We don't know exactly how many terms there are, but yeah, I mean, surely there must be at least several 100,000. And each of those might be associated with millions of pages, right? So this is a very, very large system for each language. Now, the index itself is going to be divided over many servers, right? So a North American data center will probably have a majority English section. It might also have significant sections for Spanish and French that are also spoken in North America, but, you know, other languages, probably not so much. Okay. Other queries that, no. So each server, right, we're going to talk about a couple things. So number one, the index entries are very big. In many cases, it doesn't make sense to store one index entry on a single server. It makes sense to break it into segments and store it on a bunch of servers so that the queries involving that server can operate in parallel. But number two, it also makes sense to mix different index entry segments on different servers. And the reason for that, imagine if you had a block of, say, 10 servers all doing one very large index entry. And suppose that there's a window of time where nobody's searching for that, right? That just doesn't come up in the searches. That's a window where those servers are all just gathering dust, right? It's kind of, Google doesn't want its equipment to be idle. So what it can do is mix up index entries as best it can guess so that over any given time horizon, there's a pretty good chance that most of the servers are going to be used for at least one query, right? Because if they're not being used for anything, why are you keeping them on? That's electricity you're burning. So there's that. So again, not only are index entries broken up over servers, but also servers tend to hold segments of multiple index entries, right? Because of more efficient resource usage. And last, queries that aren't in a locally supported language, most likely going to get kicked to a different cluster, right? So what could happen if it's not in the local language, chances are Google is going to forward the entire query, right? So if you're in Tokyo and you enter in some English language query like, where can I buy an orange tree, right? They're not going to have that cached in Tokyo. They're going to say, oh yeah, we'll send that to LA. They can tell you where to buy an orange tree. Okay. And then the LA data center can send the results back. Anyway, so when a search query is received, what's going to happen? The system is going to first perform semantic analysis to identify which index entries correspond to the search term. So you enter in a long string of text, right? For example, where can I buy an orange tree? Google will eventually recognize orange tree as a semantic unit, right? You don't mean a tree that happens to have the color orange. You mean a tree that will produce oranges, the fruit. Anyway, it's going to handle that. Okay. Now, as far as traffic inside the data centers, this is a little bit more advanced stuff. I'll try to tell you a little bit about what's going on. The big thing here, Google wants to, number one, make sure that any hardware that's on is likely to be used. And number two, make sure that it's used efficiently. All right, so I'm going to start off by drawing a road. And I'm going to give it a little bit of perspective because I'm feeling like an artist today. All right, so here we will very shortly have a 4-lane highway. And I'm going to draw a really shitty car. This is better than you would think. All right. It's still pretty shitty though. All right. So this is our car. Got it? This is a car. Now, what is the most efficient arrangement? Suppose you have 10,000 cars that you need to get point A to point B. What is the most efficient way to do it? Would you have them all travel in the same lane? No, that would be stupid, right? Would you have each car occupy one row with nobody on either side of it? No, that would be crazy too, right? Oh, you fell for it. I wasn't trying to trick anybody, but if we did it like this, we're leaving a whole lot of open space on the road, aren't we? Don't want to do that. Right? Everybody sees that, gosh, we could pack a lot more cars in there, right? So what do? We make sure that for every length of car on a road, every lane has a car in it, right? That's what we would do. That is the most efficient way to get all these cars, right? So there's always going to be cars, maybe not quite bumper to bumper because that creates congestion problems, but for sure, right? Every lane is going to have a lot of cars in it, right? Every lane is going to be pretty much cars end to end. Agreed? Okay. So now, instead of lanes, think that the lanes are servers. And instead of cars, think they are tasks to be processed, right? Looking at some portion of the index. Now, what Google wants to do is basically have an arrangement where every server is reasonably busy doing tasks all the time if it's on, right? Because that way it gets the most work done fastest, right? You don't want to assign all the tasks to one server because then the other ones are just gathering dust. And you don't want to have servers idle when they could be doing something, okay? That's what these slides are about here. So I'll talk a little bit of detail, but you know, that's the big picture idea. Okay, so first of all, the servers are going to be organized into tiers, right? Groups doing the same thing to handle queries in parallel. So for any search query that comes in, the servers are already going to be pre-designated as far as which ones are going to handle which sections of the index and such. Large index entries can be broken into shards, basically segments, that are stored separately, processed separately on different machines. Now, for better parallel operation, pages that are stored in multiple tiers still have the same shard number. What that means is it's a more efficient arrangement. If there's a page that's going to be involved in a search query, it's going to be in the same lane. So suppose there are 2 roads, right? 2 different tiers, 2 roads, and there's a page that's involved in one of them. For better organization and planning and knowing who has to do what, if a page is involved in 2 tiers at the same time, it's going to be in the same lane. So when the query processing comes up and it's involved in multiple tiers, Google still knows, oh, the operation is going to be confined to lane 1. Because otherwise, right, it becomes harder to plan. It becomes harder for Google to plan because, oh, we're running a query on this lane on this road and another part of that same query in a different set of lanes on another road. It's just going to be hard to do. So Google wants to allow, basically easier scheduling, and that's one way that it does it. Now, the other question, how many machines should handle a query? So you might say, gosh, why wouldn't you throw on, all the machines you can for every query? Well, number one, that's not really a good long-term solution because you can always add on more machines, right? There's got to be a point when you stop. So suppose, we can go back to our parallelism. Let's see if it holds it. There we go. Okay, suppose we have a task that we want to break into 5 pieces, right? Now, what I haven't mentioned, this breaking takes a little extra work and time. And this combining takes a little extra work and time. Okay, there's no free lunch. So suppose this is what happened. I'm still getting used to the keyboard on this. Suppose a query on one machine would take 10 seconds, right? Whatever, it's kind of a big query, it's going to take 10 seconds if you do it on one machine, plus 0.2 seconds for the extras. Okay, so that, which in this case would be 0, right? In this case it would be 0 because there's no breaking. But all that network, all that breaking apart into segments and sending it over networks and recombining it at the end, it's going to add a little bit of extra time. Suppose on 5 machines, it takes 5 seconds plus 0.2 seconds for the extra. Okay? No, 2 seconds rather. So that looks a lot better, right? On 10 seconds, it could take 1 second plus 0.2 on the extra. But eventually, no matter how many machines you break it up across, it's still going to take that extra 2 seconds to do the breaking up and the recombining. At some point, you have greatly diminishing marginal returns, right? So you can't just endlessly add machines into the mix and have a substantial increase in time. And the other thing is, users care when it's a difference between like 0.4 seconds and 2 seconds. If it's a difference between 0.35 seconds and 0.34 and it costs you twice as much money to do it, it's not worth the trouble, right? It's not a difference that people are going to notice, and it's costing you a lot more. All right, so anyway, we don't have to make that decision, but recognize that when Google does take these queries and break them apart, there's a little bit of extra work involved. And at some point, Google's going to say, you know what, we have done enough parallelization here. We don't need to do it infinitely. Okay. Now, as far as indexing itself, Google doesn't reveal a lot of the details, but we can read its older patent documents. So, just like with two-phase commit, I'm going to save you from most of the misery of, let's see, now that bumped up that time. I don't know why it does that. Sometimes it does, sometimes it doesn't. I'm going to save you from the misery of this, but interesting thing, we are now all at a point in the course where you should be able to read that title and actually have a rough idea of what the document is about. You could say, query scheduling using hierarchical tiers of index servers. You're like, yeah, okay, I'm kind of ready, right? Now, this article is pretty long and tedious and jargony, so I won't get into it, but I'd just like to point out that, see, we're learning stuff. Okay. So the point of this whole document is basically coming up with a system. This is also 2007, so it's the pre-semantic era. This is how Google used to decide which term combinations made the most sense. And they go in great detail about the point calculations and all that, but we don't need to do that. What we are going to do is cover a couple simple examples. So first one, suppose somebody enters in the phrase New York restaurants, right? Clearly those words could be combined in different ways, even if we only consider adjacent ones. It could be all 3 separately as separate words, unrelated. It could be the semantic unit New York plus the word restaurants. It could be the word new plus the semantic unit York restaurants. or it could be one whole thing, New York restaurants. Okay? Now, Google understands that these are all possibilities and that different three-word combinations might fairly be rearranged in different ways, right? You can't just say, well, first two makes more sense than the last two. Well, Google has a point system based upon, all the information it had to work with there. And so they had their scoring function. But basically, what it was, so if we look at some of this, right? Basically, extract the initial set of candidate phrases, the combinations that actually work, identify valid phrases based upon the document data it has. So it looks and sees how often do we actually see these things in our documents and how often are users searching for them. Remove ones that are redundant or unnecessary, and basically have some rules of thumb for how you might recombine them and pick what the best ones are. That's what heuristics are. Okay. So anyway, Google had a plan. Now, this one, for example, we'll just look at it. The quick brown fox jumps over the lazy god, right? What do you think is a sensible combination there? What are two words that would naturally go together in an index, probably? Brown fox, probably, right? Or even quick brown fox, I would accept that. That could be defensible, right? Also lazy god, right? That's like a thing. But and maybe jumps over. But if you say the quick, that's probably not going to be in there. Or over the, probably not going to be in there. Or the lazy, right? Those things probably not quick brown either. That, you get the idea. Unless it's like a thing about UPS or something, I don't know. All right. So you get the idea that Google has this kind of way, a search phrase comes in, Google has to figure out how to decompose, how to parse it into the actual terms that are going to be used to define which index entries are chosen. Okay? All right. Now again, the problem is if Google considered every possibility, then the really big problem is basically Google would need to use a whole lot of extra servers in order to actually do this process, right? Which they don't want to do, because why? Slower and more money, right? It would either be slower with the same amount of hardware or require more money, in terms of electricity and hardware to keep the speed the same. So they really don't want to do that. Other thing they do, the analysis sequence, they talk a little bit about that in the patent document. And again, it's a bit advanced, but Google does pick a sequence in order to make things go faster. So for example, suppose I do a query with a very unusual term and a bunch of common terms. If Google looks at the very unusual term first, that's going to very rapidly narrow down the space of possible matches, right? So Google's not going to have to think too hard as far as all the other terms. Whereas if it says, oh, I'm going to comb through this one long list and this other long list and this other long list, do all the ranking on those, and then combine it with this very short list, it's much better to have the very short list first and see if any of those other pages are related to it. Okay, so that's that. It's like going into a restaurant, and suppose the restaurant suppose it's all about soup and they have 10,000 different kinds of soup. And you could look at the whole list of soup and then figure out which kind you want. But then suppose that maybe you didn't really want a soup, you wanted a burger, but they only had 5 kinds of burgers. And you say, okay, it's very easy to look at that burger, and I just look at all the soups that might go with a burger that I'm going to get. So I don't know. Food, because I haven't had lunch, so I'm thinking about burgers and soup. Okay. Okay. Now we know Google has lots and lots and lots of page documents and has multiple copies of each, right? And like we talked about way back when about Facebook, web pages do not have a fixed structure, right? All the elements of a web page can be combined in arbitrary ways. So it doesn't make sense to store them in an ordinary relational database, right? That was one of the, does that ring bells? That sounds familiar? Yeah. Don't want to store web pages in an ordinary relational database because they don't have a stable format. However, the extracted data does have a fairly regular format, and you can store that in more or less a relational database. We'll talk about that in a minute. Okay, but this document storage, it's very, very large. It's its whole separate system. But way back when, right, in the early incarnation of Google, basically Google had to look through the documents itself. Before they were actually, had everything pre-extracted and ready to go, Google would look through the documents and say, oh, let's figure out what we can get. The system still works if you talk about, now we're talking about extracted data, but the early backrub system, they just looked at the documents themselves. Now, Google would analyze all those relevant variables, and there are, hundreds of them. Eventually, Google figures out the best matches. The users get a blurb of text, right? It's going to be the title and a little bit of text about what the page is about. And if you read the patent document as well, again, there's various layered rounds of page ranking on top of this. Before Google actually pulls the documents, it looks at the match strength of the search terms, right? So not only are the terms on the pages, but are they next to each other? Are they sequential, or in the same order on the page as they are in the search query? And then afterwards looks at the document itself, right? But now, of course, Google has all of this extracted page data, and we really don't know, okay? As far as outsiders know, Google uses the same kind of methodology, the same kind of process for any kind of page, although we really don't know, right? That's their special sauce. So, but what we do know is they extract a whole bunch of data from the page that they use to do ranking. So the obvious ones, they need the title and the blurb that they're going to use. They want to have that ready in case they pull the page. But they also have literally several hundred other factors that they use. So for example, they could use web objects. They could use, like shopping carts, like images, like videos. They could use the metadata of those things, like what the pictures are about, what the videos are about. They could have any other stuff, like how often the page has been updated, whatever, okay? And again, this is a generally uniform structure, which is compatible with relational databases. So as we'll see, Google made a few tweaks, but it's a fairly relational database. It's an extended relational database is the correct way to say it. And as we said, documents also get stored in their original form. The reason why Google stores the originals of these web pages is in case Google wants to tweak its algorithms, right? If they say, hey, we're thinking about including some new variables in our system or combining them in different ways, they need to go back to the original pages and extract that data to do it. Okay, and they're constantly doing that. Again, because web pages don't have an inherent structure, this kind of NoSQL system is a sensible option, right? Some kind of large-scale document storage where they're more focused on, not having a lot of empty space in the database. But for the rest, for the extracted data, Google uses Bigtable. And in Bigtable is a special kind of database called a sparsely populated database. But we'll see there's some interesting things. Also, every record in Bigtable has a timestamp. So Bigtable, for every record, is going to be the data extracted from a particular web page. And so you're going to have all that extracted data, and then at the end, a timestamp, so that if a new version of the page becomes available, Google can be aware of that, can include that also as an extra one in its system, or can replace an older one if necessary. But Google can have different versions of a page in its system and recognize when a change has happened. Okay, as far as Bigtable itself, has some interesting things. So number one, rows that Google considers to be related to each other are stored close to each other, right? In the same chunk, and same near each other in memory and on the same machine. And this makes it much easier for Google to do batch updates, right? So anytime Google wants to, update a set of pages, they're going to be right there. It doesn't have to scan through its entire database to do it. It could say, oh, yeah, I'm doing an update on this little batch of pages. I'll get that done really quick, okay? Second, column families. So remember back when we talked about relational databases, they had this property called atomicity, right? And atomicity means that a field in a database refers to one particular thing, okay? Well, that's not really realistic for web pages, because a web page could have, for example, many images or many videos or many of any other kind of web object, many links. So a column family basically provides a pointer to another list. So if a page has 100 images, say, you don't have to allow room in the record for those 100 images separately. You can have some reference that says, oh, if you want to find those images, here's the pointer to where they're stored. I'll tell you where to find them, okay? And that allows this basically relational structure. If you're not interested in those images, fine. You know, you don't need to worry about them. You can kind of skip over that. But it means that every record within Big Table proper is going to still have the same size, making it faster to look up records. Third thing, sparsely populated. They're going to be, since Google has several hundred factors that it's including for web pages, there are going to be many pages that have basically null entries or the equivalent of zeros for a lot of those. For example, if Google has a column for shopping cart, basically only retail sites are going to have a shopping cart feature, right? All the sites out there that aren't retail are not going to have an entry for that, right? And there's going to be a lot of other things like drop-down menus that retail sites often have, non-retail sites rarely would. So Google doesn't want to force all these kind of different types of sites to have exactly the same space and, you know, just hold a bunch of zeros. So if there's a record that has a big cluster of empty entries in it, Google has a way to compress them, right? So instead of saying, I have 800 factors that I'm going to include in this database, but a typical page maybe only uses 40 of them, Google can say, oh, yeah, these 40 are included, and these other sets, you know, are basically, there's nothing in those. So it's a way of saving space, which again becomes very, very important when you're talking about saving, you know, trillions of pages. Okay, so those are the properties of Big Table. Now, as far as spelling server, this brings us to our last thing, which is this whole spelling bit. So what spelling servers do, they receive the original search queries, and they identify misspellings by comparing query ranks. We'll talk about what query ranks are in just a moment. And then they return a list of likely options. So if you've ever misspelled something or just entered in an unusual name in Google and it says, we think you meant this, showing results for this, right? Did you really mean what you can on that, okay? Now, Google actually developed this. Part of it was, a big part was Google had something called the search appliance, currently pretty much phased out, right? They still exist. Probably a few businesses still have them there, but Google's trying to get all these businesses to do the same stuff in the cloud, and I imagine most of them are. But back in the day, the search appliance was kind of a neat thing. It was a little server that could store, you know, several million documents, and you could index them and find them quickly, right? So it was basically a digital filing cabinet that was extremely well sorted and easy to search. But one of the obvious problems that comes up, what if there's a spelling mistake, right? So I'll give a little historical thing. You guys all remember 2016, there was that whole thing around Hillary Clinton's emails? Yes. And you remember that eventually she had to supply like some 30,000 to the FBI, and then she said, well, you know, most of those are personal, we're going to get rid of them, right? Does that ring a bell? Yeah? Okay. And then a little while later, a few hundred turned up, right? And people were like, what is this? Why are there extra emails? Well, as it happened, those few hundred that turned up in the final search, those were ones that had misspellings for some reason, right? They had gone through the search to try to identify ones, you know, that they were going to pull. And the ones that they missed were ones with spelling errors, so they didn't show up in the initial search. Now imagine if you're a business and you have some important paper that's written by the CEO, but in the tags of it, somebody misspells the CEO's name, right? They, you know, their fingers flub on the keyboard and they replace a C with a V. You're never going to find that unless you have spell correction, right? So yeah, that's, you know, it's a very important thing. Anyway, so for the last 10 years or so, Google has been correcting user spelling. And again, sometimes Google thinks that you have definitely made a mistake, right? It is said, we don't have any index entry for this word. This word is super weird and we don't like it and we think you're just making shit up, okay? Of course, sometimes it's just correct but unusual words that are very popular, similar to popular search terms, right? So for example, if you have a name that is close to a person's name and you try to Google for yourself, you're probably going to get a lot of results on that, right? This is I'm not sure why, but in my younger days, I would very often get confused as a Lindquist. I don't know why, but it was like and my brother, he would like, my brother's name was Stuart, and he would get a lot of mail address. It was spelled with a U, but he'd get a lot of mail addressed to Stuart with an EW. I don't know. Sometimes people mess stuff up, right? Anyway, Less usual words, very similar to popular ones. So same kind of thing. Now, how spell correction works, right? Google has to do this in an automated way. They don't have some guy back there saying, oh, I think you spelled this wrong. They have to come up with some automated system that's going to work reasonably well for everybody. And what they do is they consider first a term's query rank. So query rank is going to be higher if a term is more frequent. That means it just is used more often in searches. That's what we mean by higher frequency there. And very rarely revised. So revised means you enter in the search term, you see that you entered in the wrong term, you go back, you edit the term a little bit, you run the search again, right? That's a revision. So a correction candidate will, number one, have relatively low query rank, and number two, will be similar to a high ranked query, okay? And that's how Google tells. It says, oh, nobody searches for this, but this term that you typed in, it's really like this other popular one. And similarity can be defined for individual words, semantic units, or just observed from sequential searches, excuse me. So for example, let's go into Google. I do have fun with this when I do it. We're gonna try to do some messed up version of University of Illinois. Okay? Work with me here. Nerversity. What the hell, dudes? All right. We're typing in Nerversity. Okay. Of, how should we butcher Illinois? Nullinois, Nullifoy? No, see, well, it's face there. All right. But if we do Nilioi, University of Nilioi, Biznago. No? Chomaga. Nilioi, your mama. No? Chinofo. Chinago. All right. We gave him an easy one there. So anyway, it's surprisingly good at figuring this shit out. And we can add a whole bunch of shit onto the end of that, and it takes Chinese. No, that's interesting. Yeah. All right. So yeah, the spelling thing is kind of fun. I do that just to ruin Google's day. I don't know. All right. One more slide. Now, last bit, indexing trouble. So how does Google handle updates in real time? Okay, because you might say, well, it's 4 in the morning. I want to go search on Google, and you don't want Google to, oh, sorry, our servers are down for, updating our stuff, right? That would suck. So first of all, as far as Google is concerned, all of this search activity is read only. And we know that problems with database consistency are only going to happen with concurrent write operations, don't we? Don't we know that now? Yeah, so if you have multiple people trying to write to a database, there's a chance something could get lost. But if people are only looking, then nothing in the database is going to change. There's not really a problem, okay? So Google basically doesn't really have to worry about consistency problems, and that makes life a lot simpler for them. Okay, second, like we talked about, the whole big table system is designed to allow frequent small-scale updates. Because why? Because table entries that are getting updated together are physically proximate in the storage media, and so it's very fast and easy. Once upon a day, I used to say, so changing anything in the database is going to be really fast and easy, like hooking up with your best friend's sister. But yeah, I don't say that anymore. That was years ago. Anyway, third, duplicate copies are always maintained locally, right? So for any part of the database, there are going to be a couple extra copies, which means if somebody's looking at part of it, that means the other 2 copies are going to be available. And we know Google does eventual consistency for the search results, just like in Facebook, right? Facebook, if there are people looking at things and they're a post on different data centers and there's different sets of likes, Facebook doesn't really care if they're not perfectly synchronized all the time. Same kind of thing with this, right? Different people looking at the same search terms at the very slightly different times might get different results if a revision is pending on one copy of the database, right? But again, this is a search engine, some imperfection is expected, some inconsistency is acceptable. It's not like you're doing big $1 million Bitcoin transactions and everything has to be perfect, right? So again, if Google insisted on perfect database consistency, eventually that would substantially slow down search results and it would, people wouldn't like it. So Google says, yeah, you know what, there's a possibility your search results might be a very tiny bit off, but number one, most of the day, there aren't going to be these updates. Number two, the updates are quick when they happen. Number three, a lot of times they're not going to be simultaneous queries in that window. Number four, even if there are inconsistencies, it's probably not going to affect the results on the first page. And five, even if it does affect the results on the first page a little bit, what are you going to do? Search is not a perfect thing. Okay, so they don't worry about it too much. Anyway, that's all I got. Have a good weekend. We'll come back and we'll do the Google advertising lecture next week. Okay.